Okay, it's just about 4:05, so I've started recording, and Susan, you can go ahead when you're ready.
Welcome, everyone. It's a pleasure and an honor to have you all here. Before I introduce our speaker today, Dr. Kim Prather, I just want to say that we're all mourning the loss of a great atmospheric chemist and former MIT faculty member, Mario Molina, who passed away this week. And I won't say more because Kim was very close to him, and she's going to say something at the very end of her talk. Let me introduce Kim. We're so happy that she made time in her incredibly demanding and busy schedule to be with us today. Kim is a real Californian. She got her bachelor's degree at UC Davis, and then she kind of did the tour of the campuses. She got her PhD at Davis, but then she went on to do a postdoc at Berkeley to become a faculty member at Riverside until San Diego stole her away, where she currently is at UC San Diego as a distinguished professor. And her talk today, she's already got the first slide up, is on a topic that's on everybody's minds, and she's incredibly in demand, along with about half a dozen other atmospheric chemists who are working to put the techniques of atmospheric chemistry and aerosols to work on understanding COVID-19 and its transmission via aerosols. So with that, I will give it to Kim for her talk. And again, thank you so much for joining us.
Okay, well, thank you so much for having me and for inviting me. It's a great honor to be giving this seminar today. And when I was I've been connected with Susan about sort of the work we've been doing and a lot of, I guess you could say, public outreach and trying to get people to understand how this virus has made its way and is so effectively making its way around the world. And so what I thought I would do is I do have a day job. I run a large center, which happens to focus on aerosols. It's funded by the National Science Foundation. It's called CASE. And so sort of, how the heck did I get involved in, looking at airborne viruses and SARS-CoV-2? And so I will start out with just a little bit of background on my normal job, and then I'll kick into sort of the work that I've been doing, focusing more on translating the science to the public. And then I'll finish up just a little bit on where we're going now that we're sort of in this airborne world of viruses, where my own research is heading now. Okay. All right. So, I like to show this, and I normally show it because I do a lot of research related to aerosols and clouds and climate. And I sort of show this as, just evidence that aerosols don't really know boundaries. They travel around the world. And, in particular, we have a very strong interest in CASE in sea spray and what comes out of the ocean. But these are, particles that can go, all the way around the world in a couple of weeks. So when I'm in the being asked constantly, can aerosols really go further than 6 feet? I often think of this figure and smile. Yes, they can go further than 6 feet. And so this has been, connecting these two worlds has been interesting. I have a really growing interest. Before this pandemic, I was very interested in airborne microbes, in particular bacteria. There isn't nearly as much known about viruses in the air. And so this was sort of a newer area for us, but trying to understand sort of how microbes are regulating the temperature in our climate, sort of controlling the health of our planet, much like microbes control the health of our body. And so I've grown to have a very major appreciation, major interest in microbes and how, those that get into clouds and seed clouds and come out of the ocean, how they're having a profound impact on our climate. And that's the case side of my life. But they span all the way from, tens of nanometers up to, 10 microns or so. Bigger than that, they don't stick around very long, so we don't think about them too much. So this is CASE. This is the team taken at the last annual meeting. It's headquartered at UC San Diego. This is pictured. This is the Scripps Pier in the background. This is the whole crew, including the advisors that were present. It's about 12 other institutions are involved. it's been going now, believe it, I mean, it's sort of surprising to me, but it's been going now for a decade. And so it's basically 10 years plus there was a 3-year period. So we have 3 more years to go. But basically, CASE has been an amazing center for me. It's helped me grow. I think I've learned a lot about leadership and how to sort of connect the dots and do things that aren't just for your own research, but to really take advantage of people from a variety of areas. The heart of CASE is chemistry. It's funded by the chemistry division at NSF, but it also has oceanographers and marine biologists, and it really spans the gamut. And that's really how you can start to address these really complex problems in the real world. So when we started CASE, we proposed basically that we were going to, I'd been doing field studies for nearly 20 years, trying to understand how the ocean was affecting the atmosphere and the clouds and the climate. And no matter what we did, we could observe things out over the open oceans, but we couldn't really separate out the ocean from the human impacts. Like no matter where you go, as I showed in that movie, there's, humans and ocean. And so how do you actually really understand what the ocean was trying to do or is trying to do before humans came along and started messing things up? And so what we proposed to NSF was we were going to move the full complexity of the ocean atmosphere into the lab where we could actually control and study how it's influencing our atmospheric composition and our climate. And at first, it seems like it should be simple, it's just salt water, but in fact, they don't call it the living ocean for nothing. It contains millions of viruses and bacteria. All signs of life basically are present in the ocean. And so when waves crash, you can see here's a picture. All of this stuff, the biology can get very enriched actually in the atmosphere. And that can have major impacts on our clouds and our climate. And so this is what we were trying to reproduce at a level where we could do the really complex system to tropospheric aerosols to really understand their properties in the atmosphere. So just to show you what it looks like to move this into the lab, this is our wave channel. It has lights. This is during a summer experiment we did last summer called Seascape. And you can see this is normally an empty, like a barn, but you can see these are the breaking waves. And we have, we're doing reactions on the headspace. We're looking at VOCs, we're looking at gases, we're looking at the species, the microbes, the viruses that are in the water versus those that become airborne. It's a massive, massive experiment when we kick these off. And we do these a lot of times in the summer. And we have a really great summer program where undergrads come from all over the United States. But I just wanted to sort of show you the scale of this setup. We take real seawater, we can induce phytoplankton blooms, and we can isolate it and watch the chemistry and how the biology actually impacts the composition of both the spray and the gases that come out over the course of the bloom. So we've got amazing insights, and we have really started to be able, the goal was to be able to explain real world processes, and we're there. I mean, we can finally sort of explain what it is about the marine atmosphere that changes those clouds and the climate. But that's for another day. I talked to Susan, I said, I'll give a separate talk on that at some point. So basically, one of the things we did in CASE, there's work published back in 1977 in Science that, viruses can get out. When those waves crash, they're hydrophobic, they don't really want to be in the ocean, they can get launched and enriched in the atmosphere. And so, there's a lot of pathogens in coastal waters in particular. And so our question was, does everything get out? If a wave breaks, do all bacteria, do all viruses get out? And so we did some early studies. This was published in 2018, looking at, this is really complex, but just to sort of show you the idea, the top shows bacteria that became airborne, the bottom shows viruses that became airborne. And these are all broken down by the different species. But the question was, do you just see sort of everything, the same concentration, relative concentration in the water and the air? And the answer is no. There's actually a lot of selectivity. Only, and you can see up in here, the red means that they're enriched in air. So only certain actinobacteria get out really, really effectively. We understand that now because it has to do with their cell walls, are very hydrophobic. Down here, the viruses are hinting that these are enveloped. We've broken them down into enveloped and lipid enveloped and non-enveloped. And the hint is that the ones that have lipid envelopes like to become airborne more than the ones that don't. But this was the very first time anybody had ever had the true breaking waves and been able to look at this transfer process. And it showed us that there is a lot of selection that goes on. And so we've continued down this path. But this is where my interest began to peak for viruses and bacteria in the air. Before I go into sort of the virus story or the communication story, I just want to sort of put a mention out that we're really excited. As soon as this pandemic sort of slows down, we're chomping at the bit because we have, in addition to the wave channel you saw, we're building another one that has winds and wind speeds up to 19 meters per second. We can also control the temperature so we can make sea ice. And this will allow us to sort of take things to the next step. We're going to integrate a large smog chamber that will be integrated so we can actually start to add in sort of the human plus ocean component. So this is SOARS. It's coming online this next year. So say we're super excited to get going with this. I just wanted to mention it because it is going to be a world-class facility that we cannot wait to be using. So background on viruses, how the heck I started thinking about viruses. Now I just want to sort of focus on a little bit on the story of how is SARS-CoV-2 being transmitted. In particular, how do we know that it's airborne and what has it required to move the public agencies to sort of shift their tone, which is still a work in progress. And so I think it's an interesting story. It's been incredibly intense. Lindsay Marr has been, she laid the groundwork, quite honestly, for airborne viruses. Without her work, we would not have been able to do all that we've been able to do. I've gotten to know her through this pandemic. As I say, I'm glad that I've gotten to know her better through this pandemic. And I've stolen some of her slides. But I've also worked with Don Milton, Jose Jimenez, and Chip Schooley's an infectious disease doctor through this whole process. We've all become a pretty big team. Plus, there's many, many more, as I'll talk about. I want to point out that there are so many newspaper articles. If you go search on Airborne or Aerosols and COVID, you will get hundreds of articles. And so this really isn't everything. It's just to kind of give you a flavor for how things have shifted around. And so I'm calling it the Reader's Digest condensed version of the story. So I stole this slide I stole from Lindsay. She showed at the National Academy's workshop, but just a general picture of how does respiratory disease get around? Basically, what are the transmission routes? There's direct contact, there's indirect contact where you touch a surface where an infectious virus might be. And then there's the two things we talk a lot about and that you'll hear a lot about today. There's big droplets and there's little aerosols that come out of us, with the focus being largely on coughs and sneezes. And as I'll talk about for this SARS-CoV-2, it's a little sneakier than that. It's actually figured out how to get out of humans that aren't coughing and that aren't sneezing and they don't even know they're sick. And so that has turned out to be a major twist in a way that this virus has very effectively been able to sneak around our planet. So traditionally, going way back, and this is something I learned from Lindsay, that basically, the medical field, if you go read the medical textbooks, it says anything above 5 microns falls to the ground within 6 feet. Anything below 5 microns can go further. So the cut right there is the red flag for those of us who study aerosols. Why would 5 microns, above 5 microns fall to the ground? We know that's not the case, but this has been in the medical textbooks for decades. And so this is where we started. So there's, sort of unclear where it comes in, and Lindsay, I think, is working on a history of how this came about, which I think our paper should be coming out one of these days soon. So I'll leave that for her, but it's not based on any aerodynamic or physical behavior that we know about. That is what I will say. So February, now we know that our leader, one of our leaders actually knew it was airborne. And we also knew that the World Health Organization Director General announced in a video anyone can go watch on the web, he also called it airborne, but it never came out in the press. You can go find it, you can go watch it. He said airborne, and then it went quiet. So the next thing we know, that's February. March, WHO posts that fact check. COVID is not airborne. This is incorrect. And so they're not just not saying it's not, they're saying it doesn't happen. It's not airborne. And so this is one of the big parts of how the public, we talk about public communication, how important it is for the public to understand. Why is the public losing trust in scientists? This is part of it, okay? So basically, at that time, back in March, we were all told, that the transmission occurs through these big droplets. They fall to the ground. As long as you're 6 feet apart, you're okay. You'll be okay. So keep your social distance, wash off all your groceries, and life will be good, right? So disinfect surfaces. It was very much about cleaning surfaces. Socially distanced. Masks don't work. Don't use up the masks. Save them for the healthcare workers. So we were told also masks don't work. And if you have any symptoms, stay home. Okay. So around this time, Wired started going, how is it in the air? You're breathing it, but it's not airborne, but it is airborne. But airborne means borne by air. Everyone was confused. And I came into this around this time in March, and I was flat out told that we're not really supposed to use that word. We're not supposed to use airborne. That is reserved, right? So how do you explain to the public and not use airborne became a conundrum that many of us faced until we decided we were just going to start saying it like it is. And that's where I will take you. So then people like Lydia Maraska and others, Lindsay was actively involved. There was lots of work going on. This was a paper that came out in April saying the world needs to wake up. It's likely in the air, it's highly likely in the air. And if we wait until we have all the data that proves it's in the air, it's going to be too late. A lot of lives will be lost. This is where there was an argument, this has been made for other diseases in the past. We should be taking precautionary measures. That's the best thing that we can do. And so, there's this conflict, between what the public health advisors are telling us to do and what hospitals and other places are allowed to do versus what scientists that study this and have studied this virus, or viruses, respiratory viruses, I should say, for decades. So this created some issues. So in May, I think I started towards the end of April, started writing a prospectus that was published on May 27th. And this is when I sort of became heavily involved. It's called Reducing Transmission of SARS-CoV-2. I wrote it with an infectious disease specialist, one of my colleagues, Chip Schooley, as well as Chia Wang, who studies aerosols in Taiwan. And basically, it was very clear at this point that this virus was getting around, was being spread largely by people that we call asymptomatic or pre-symptomatic. They have no symptoms. And it's not from coughs and sneezes, it's just from speaking. Produces tons of aerosols, a lot more aerosols than droplets. So what can you do? You need to wear masks. Everyone needs to wear masks. How many times have we said that, right? So masks are bidirectional, and we can block, but the real goal is to block the source, to shut off what comes out of someone who doesn't know they're sick. They're just walking around in the public. And so this figure has been used everywhere. It's amazing around the world. And this paper has been downloaded now about 1.6 million times. So it's had an impact, but it's still, the debate still raged on, is what I will say. So what we said at the time was it's aerosols, it's through inhalation, which lets things get deep into your lungs. It comes from people who speak or sing. The louder you are, the more aerosols you produce. Those can contain infectious virus if you're infected. Indoor risk is absolutely the highest. Basically all the cases, most of the cases I should say, have been exposure that you can trace, have been indoor events. There's been a couple, not that many outdoors, because outdoors just massive dilution acts in your favor. Basically one of the things we've been pushing really hard is that masks need to be worn indoors. There is no safe social distance indoors. Even if you can be 6 feet apart, these aerosols, you've been in the room with a smoker, it builds up over time. You can fill a room with aerosols. And if you inhale those for an extensive period of time, your risk of being infected is quite high. So the mode of exposure actually turns out. So if it's contact, and you get it on your hand and you touch your nose and get it into you that way, versus you inhale it deep into your lungs, the severity can actually be really, much worse through aerosols. This is another motivation to wear masks. If it goes super deep, it can bypass your immune system and then start to replicate. This one replicates 3 to 5 times faster than the original, the SARS-1 virus that we studied in the past. So it starts taking off. Your body doesn't know it's under attack until it's kind of sometimes too late. But the key is that masks block the emission and reduce the dose, which can either make you not get it, not get infected, or it could basically reduce the severity of the disease if you do get it. If you just get a few viruses in, we're still trying to figure out how many is enough, but this masks are our main barrier right now that are so important. So public messaging 101 took off. I took my public messaging experience from climate change and ramped it up. It was sort of like climate change communication on steroids. I learned along the way even more things on how to get things through to the public with simple messaging. We don't know everything, but we know enough to fix it. So let's do that. And I've become really, well, I've worked a lot with CBS Chief Medical Correspondent, Dr. LaPook. He's been part of the team of trying to get this message out. I did CNN, all of us have done at this point hundreds. And if you added them up, it's thousands of interviews on this topic. On August 6th, I had kind of poked at Tony Fauci a lot about this 5 micron, enough to where myself and Don Milton, Lindsay couldn't make it. We briefed Tony Fauci, and I'll talk about that. But basically the point, aerosols go much further than 6 feet. The medical textbooks are not correct. You people maybe have heard them, and I'll come back to this. And we also created this fact. We were getting hit with so many questions through social media that we created this fact. And if anybody wants the connection or the link, I'm happy to share that. But this has helped schools and businesses and people in a major way. I mean, in some ways, and scientists, this grassroots, we figured out how we can help the public. They weren't getting the guidance they needed elsewhere. So we kind of kicked into overdrive and have been helping people as much as we can. I was told not to use the word airborne, as I mentioned. I was told that it will create fear. I can say that through my hundreds of media interviews, I have not created fear. And I think all of the aerosol scientists would say that. The public really appreciated clarity. And, the big message is, once you acknowledge it's in the air, you can fix it. Aerosols are easy to get rid of, relatively easy to get rid of. But if you keep denying they're there, we're going to stay in this pandemic for a lot longer. So stepping back, what is the evidence? Why are we so confident, of this being airborne? So there was a virtual workshop. We had a 7-week in the middle of this craziness. We organized, Lindsay was on it with me as well. We organized a workshop. We had, 7 weeks, started in July. It came up in August 26th. And we had a big discussion of everything we know about this virus. And so if you're curious, I encourage you to go look at it. It's 11 hours, but it has everything you want to know about SARS-CoV-2, at least at that time. Key is size plays a role. 5 microns isn't cutting it. That doesn't describe anything. We basically proposed agreed, I should say, the scientists at this workshop, we all discussed, well, if it's not 5 microns, what should it be? We picked 100 microns to separate aerosols and droplets. Keep in mind, this virus is not naked. It's, if it was, it's about 150 nanometers. When it's encased in this dried respiratory material, which I'll talk about a little bit on the next slide. When it's encased in that, it's about a micron or 2, somewhere in there from speech. The big drops are big. And so we picked 100 microns as a much better cut. And this is because it explains the airborne behavior. Things below 100 microns can travel much further than 6 feet. Things above 100 microns will fall to the ground within 6 feet. And things below 100 microns can get inhaled. Things above 100 microns cannot. So if the ultimate goal is to control it and to protect you, then it makes sense to define it based on the mode of transmission. So that brings me to this, and this is a slide that Lindsay made that she showed at the National Academy workshop, that large droplets, can be sprayed. There aren't very many. So think of them as like little mini cannonballs. They have to fly on this trajectory. Jose Jimenez used Angry Birds. They have to fly and hit just the right spot. And there aren't very many of them. Whereas aerosols get inhaled, and there's, for every droplet, there's hundreds, I should say, of aerosols. And so, basically, distinguishing it, making the cut at 100 microns, this was a big outcome of that workshop. Composition wise, it's salts, things from your respiratory tract, proteins also, but things just sort of dry down. This is an image. Again, this is, sort of looking at it. Why is it a micron and not smaller? This is what else is there. So thinking about what gives you these different sizes? Is there really just a continuum of sizes generated when you speak? The answer is there's actually modes, different size modes. It's not quite a continuum. It's certainly not a dichotomy. You can't just say, here's the drops and here's the aerosols. I mean, in some ways, I guess you almost can if you look at the break right here. But the interesting thing about this is work that Lydia Maraska published in 2009, is that each of these, when you fit this, you actually get different size modes, and those are coming about from different production mechanisms, which means that, aerosols in the small size range are coming from, deep in the lungs. These are coming from when your vocal cords vibrate. It's bubble rupturing, very much like the surface of the ocean, which is interesting. It can enrich the viruses in the smaller sizes. And then your mouth, your saliva also has the virus. And so, depending on what size you inhale, basically you could get very different compositions when you look at that. So basically, if you look at sort of the definition, aerosols, the way WHO defines it, they're just this amount, whereas the ballistic drops are, up in this larger size range. But if you look at just the aerodynamics of what we know in still air, okay, this is not moving air, this is just still air. You see all these different sizes. If it's a half a micron, it could take 41 hours to fall to the ground. Get up to 3 microns, it's 1.5 hours. 100 microns will settle in seconds. And so that's, sort of that size is where those become the boulders that fall to the ground, can contaminate surfaces, but you're not as likely to inhale them. So this is a figure that when we were going to talk to Tony Fauci, Lindsay put together, which is really, this was the key slide that I showed him. And basically, if you start at a height of 1.5 meters and you look at 5, 10, 20, 30 micron particles, what you see is that in a low indoor velocity of 5 centimeters per second, so pretty still air, but not completely still, you can see that a trajectory of a 5 micron droplet is 100 meters, a lot more than 6 feet. If you have moving air, there's a lot of drafts in rooms. You can see at 20 centimeters per second, it could go 400 meters. So that's a 5 micron. Similar things you'll see for bigger, up to 100 micron, they can go much, much further than the 6 feet rule that we've all been told to obey. So one big day, I remember this day very well. I did the briefing on August 6th. On September 10th, Dr. Fauci started talking about these wild, crazy aerosol physicists that hounded him. And that basically, he announced that they were wrong, that it had been incorrect. This 5 micron break was not correct. It was inaccurate. It wasn't explaining anything. And when you look at the break correctly and the behaviors correctly, the bottom line is in red. There's much more aerosol transmission than we thought. And so this was a big, big breakthrough because he's, as you know, the head of the coronavirus task force. He also works very closely with CDC, and he's just an amazing person. So getting him pulled in was a big part of the equation. So coming back to, if we now take this into account, now you see that aerosols are almost all. The droplets are now much smaller fraction. And, as much as we've been under pressure, we've been told, oh, prove to us that it's aerosols, prove that I'll show you the proof, but, there's a very high bar to change this because, basically they would accept that it's in droplets without the proof. And there really is, there's a really good paper by Kevin Fennelly that says, I searched all the literature, I can't find proof for droplets. But for aerosols, if we didn't have the proof, people really didn't want to accept that it was airborne. So another part of the spread has to do with some people, just when they talk, they produce a lot more virus. If they're sick, they can shed. Some people just happen, it depends on the stage of infection and just the person can shed. This looks at sort of the bioaerosol particles that come out of different people, and you can see there's a huge range. And one of the interesting things is this thing called the Pareto principle, which basically says that about 10% of the people that are infectious account for 80% of the infections. So most people don't spread it, but there's a handful of people, and I should say conditions, that lead to these massive, what we call super spreader events that can only be explained by aerosols. So knowing that, then we have, if we just acknowledge that, we can get clear that, like, if it's leading to this, then we need to think about what are the highest risk locations, places where people are yelling, grunting, exercising, not wearing masks, indoors, low ventilation. And so that's shown here. This is where we see most of the outbreaks are gyms and restaurants and bars, and this is why. The Tokyo trains, they don't talk, and they have no incidents of transmission. And so this is a call center in Korea where all the blue are the people that got infected on one side. And again, the message, the key message is we share the air. These people didn't all touch the same contaminated surface. They breathed the same air though. And so this is where you can explain these very large super spreader events that we see in camps and choir practices and nursing homes and meat packing. They all are really, just cumulative. The epi sort of points at, this is airborne. Okay, so as a function of size, how do we know the virus is in the smaller particles, smaller aerosol particles? Well, some of the first work was done, basically looked at the RNA. So this is not saying it's infectious. This was the first step, just finding the RNA that says it's in, and it's in these smaller particles. And indeed, that's where you see it, is more in the smaller sizes. And then the big study was Lednicki. They came up with this. It turned out that this virus is kind of fragile. And if you pull air onto a piece of filter paper or just partially pull air over it, you'll fragment the heck out of it. And so it's hard, it doesn't remain infectious. So this is a tool that was developed by a close friend of mine, Suzanne Herring. And basically it condenses water on them and then collects them into solution. So it's a much more gentle approach. And this has been being worked on for years at Florida. And they were able to show that they actually could collect in the air infectious virus in the hospital that had gone over, again, past the 6 feet. So yes, it's in the smaller particles, and yes, it can remain infectious. So we continued to add more pressure. There was a letter that we submitted. It was to Clinical Infectious Disease, came out in July. Lydia and Don Milton led it. 239 of us signed it, saying it's in the air. This is actually a great article, opinion piece that Lindsay wrote. Yes, coronavirus is in the air. We just continued to just hammer it every day. We were tweeting and social media, it's in the air. We've got to, we need the public, health experts to say it. And so CDC, WHO has lagged. CDC has moved forward, I would say. In June, is largely still saying it's surfaces. In September 18th, this was another big day in the story. It came out saying that it's airborne, and it comes out people when they cough, sneeze, sing, talk, or breathe. And this is thought to be the main way it spreads. And there were celebrations in the streets, at least on Twitter. Everybody who's, we finally finally the public is being told so they can, we can protect people, right? We were so excited. And they retracted it. Just as quietly as it went up, it quietly came down. And so, we waited, a lot, basically when it went back up, it went back to the old one. And then the world waited. Well, at least the United States waited. This was a depressing day. So we had a good weekend, let's say that. So then back comes Dr. LaPook and says, let's work on a statement. We'll just get out how it works. And so Lindsay and Don Milton and myself and John and producers and writers, we spent an entire Sunday writing, like, this is what happens. And this was, posted on the CBS website. It, basically was on the news. Again, just continued this sort of push that we've got to, if CDC and WHO aren't going to tell the public the truth about what's happening, then we are. and because we got to fix this. So this was a big part of it as well. Finally, on October 5th, after this conversation, sort of became clear, I asked the science editor-in-chief, Holden Thorpe, would you, like, if I were to write something about 100 microns being the break and we were to clarify this, would that be something that science would be interested in? He says, submit it. So rushed, put it together. Lindsay and I wrote it. Chip Schooley with others, MDs, as well as Don Milton. This was the hardest 300 words we've ever written, but we poured over all these words. We updated the break to 100 microns. We pointed out that, think cigarette smoke versus cannonballs. We just said we have to harmonize our language so we can, part of getting the public to buy in and do the right thing is for them to understand. And so that's what this piece was. And so within, basically within 7 minutes, literally, of this coming out, CDC put out their new piece of information. They backtracked. They said, you can see that it says COVID-19 can sometimes be spread by airborne. And so, but they at least got airborne back in there. Aerosol, the word aerosol disappeared. And so, this is where it sits right now. I can tell you a little bit that there's a glimmer of hope that we're going to work with them on the language to try and get all of this harmonized. We're getting very, very close. Today, I'm feeling pretty optimistic. So, basically, airborne transmission is the dominant exposure pathway just based on simple probability. This isn't being produced in sneezes and coughs. This is by people who, as I said, didn't know they're sick. They produce aerosols, which go much further. It has just found this sort of magical way to get around the planet. And, basically we have to acknowledge it. And if we can acknowledge it, we can fix it. So, once we acknowledge, then we have to think about masks. We need to wear masks at all times indoors. If someone else is in that room with you, everybody needs to wear masks. This applies to schools and businesses everywhere. But again, it's fixable. Ventilation, filtration, this size is relatively straightforward to remove. A micron, that's pretty easy. Outdoors is much safer than indoors. So for those of us in California, we're trying to move as many things outdoors as we can. A lot of places, I just want to point this out. This is fluid dynamics simulations that was just published that basically, shows what people are using. This came up around the last debate. They put up plexiglass barriers in schools. They're doing this, and buses. They're doing this. What can happen is, same thing with face shields. Aerosols just flow right around, and they can actually pool up and concentrate on the other side. So barriers is not what I would say is the best solution. The best solution is to clean the air. And so the shift has to move from cleaning surfaces to cleaning the air. For people who can't afford it, you can basically I have these in my house. You can buy a box fan and slap a MERV 13 filter on it. There's fancier ways you can make a little box and get more surface area. There's other tricks you can play, but this really lowers the concentrations of particles. And if they had virus in them, they would get pumped out through this filter for $40. You can do this. And so this is something people are looking at for schools and for people who just can't, afford an $800 or $1,200 air purifier. So this is 100 years ago. These are kids at school. They figured this out. We just did it again. But, we have repeated history in a kind of a clunky way, but we're getting there. They open the windows. That's the simplest ventilation you can have, is just to open the windows. The key is just to be smart. Right now, especially if you're in a community that has high spread, the numbers are going back up again. In a lot of places, just avoid high risk indoor environments. And if you do have to go to the store or whatever, wear your mask, get in and get out, because length of exposure is also important. Face shields alone, they don't work by themselves. You have to have a mask underneath. So should we be surprised that it's airborne? No. You can look back at a lot of respiratory viruses after the fact were proven to be airborne. SARS-1, the one that this looks kind of the most like. There was a outbreak in 2003 in the Moy Gardens, where basically they pointed out after the fact, retrospectively, that this was an airborne virus, and it actually been launched out of sewage and had become airborne. And so, the push was, we need to take this seriously. You can look at the modeling they did. It was in an apartment building where the outbreaks occurred. They basically only certain buildings and the people on the upper floors got it. And so it had to be airborne, and that's how they sort of proved it. But it was linked at this time to sewage. Again, the same idea. Nobody wanted to call it airborne. People tell me then people think of contagion or whatever. Maybe I've never seen it. I don't think I want to see it. But basically, it's going to be seeping out through the walls and everywhere, and people are going to get scared to death. I have not seen that. I just think that the public deserves to understand. So the last thing I just will touch on quickly is where we're going with airborne viruses. So there is a lot of sewage. There's tens of millions of gallons of sewage that go into the San Diego Ocean. When it's rainy season, it's really a lot goes in. There's this untreated raw sewage that comes across the border. When this happens, we see these beach signs: don't swim, don't surf. But nobody had thought about the air. So we started doing this in 2017 with oceanographers. We put dye into the surf zone to see how, does it just go out in the ocean and get diluted? Or does it actually get trapped and get airborne? So we looked for the dye using air samplers, and indeed we could find it all over San Diego County. Excuse me. So you can see that on days where we saw it in the air, it got trapped along the coast. This is the dye field. On days where we didn't see it in the air, you can see that it did go out in the ocean and get more diluted. So our hope is that we can start to understand these pathogens and different things influencing the health, human health. Sorry. Okay. So when the pandemic came along, excuse me, we, basically contacted the NSF. We said, we have sewage going in the ocean. We know that SARS is in sewage. Can we actually detect it in the river, the Tijuana River? This is the Tijuana estuary. The sewage treatment plant's over here. It flows to the estuary and then dumps into the ocean. So we got an immediate very quick funding from NSF to actually start to look for this virus, SARS-CoV-2, in the ocean, in the river, and in the air. And this is ongoing. I'll tell you, we found it, in the water. We have not so far found it in the air, but we've done this all under dry conditions. So as winter comes about, we expect we will be looking like crazy in the air at that time. The last thing is kind of an interesting slide. I'll just quickly make a point is this is from, again, 100 years ago. And it looks kind of similar, basically, it spread through speaking and coughing. Please abstain from staying in closed spaces. Keep open all day the windows. It's kind of the same thing we're saying now. I love this one down here, though. Keep your mouth clean, and in one word, follow the advice of your doctor, and ignore ignorant people who invite you to drink alcohol or consume tobacco as preventative measures. So we're repeating history in lots of ways, and so but we're luckily learning a lot. And so I'm going to stop there. I just know that Mario had a 15-year time. This is the hard one to look at. It's been a rough week for a lot of us. He was a major mentor. I would say that what you just saw, me pushing and pushing and pushing and not getting pushed back, but just pushing to not just be satisfied with the science, but to try and get it to solutions that would help people. I got it from him. I watched him do it, and he did it. He protected everyone, the earth and people, in an amazing way. And he was a big, big supporter of mine. We were very close. And so, so this was a celebration we had for his 70th birthday. I think many of you were there. It was a very, very special day. I'm really glad that we were able to do that. And it's a big, big loss. And I just can't say enough about how great a person he was. He was a great scientist, but he was an even better person in every way. So on that night, we even got a green flash, which is really special. And that we always joke that it was Mother Earth, celebrating as well, because as you know, Mario was one of her biggest, I should say, champions. And so this just shows, the big celebration we had, everybody stood up, but I love this picture because it's Mario's face of just this kind, gracious look as everybody was applauding him. And it's just something I'll always remember. So I'm going to stop there and I'll be happy to answer any questions.
Thank you so much, Kim. That was amazing. I guess I'd like to encourage everybody to unmute themselves and just applaud for not for Kim, but also for the other people who are on this call who have worked so hard on it. So thank you. We now can take a few questions. So you can either put them in the chat or unmute yourself and go ahead and ask them. There's been some discussion in the chat about sizes and humidity and such, but if people want to continue that with Kim, they're welcome to. While we're waiting, I guess I have a quick question, which is, can you talk to us about goggles, Kim? I mean, I understand because Prasad taught me that we have to think about the aerodynamics of your breath pulling things in, which I get. But we could also walk right through a cloud of particles. So do we need goggles as well?
Yeah, I mean, it's glasses, goggles for tight fitting for sure. And I didn't, I've really focused on the mask thing, and I always kind of honestly forget the goggle part, but yes, because, they can, especially if you're, people do cough and sneeze, and if, and there are, a few bigger droplets hovering around, and you can get, Don Milton has informed me many times, you can get infected through your eyes as well. So yeah, thank you for pointing that out.
Well, it's such a struggle to get people to put their masks on. We're probably not going to complicate it with that.
Yeah, it's been a hard message, to get people to put them on and wear them right. It's become the chin diaper or whatever we call it. It's just crazy.
Okay, Prasad Casablanca has a question. Prasad.
Hey, Kim, great talk. Thank you again. One comment on the goggles. I think it probably helps with droplets, but I'm not so sure with aerosols. There's some work that suggests that eyelashes and all, are the airflow is directed such that these particles, these small aerosols, don't just drift into your eyes. But my question was, we understand so much more about this transmission now through aerosols. How close do you think we are to doing quantitative risk assessments of infection in specific indoor settings, which is ultimately what people are looking for to figure out how to reopen? In terms of, we'll say that this is a risk we're willing to tolerate. How close do you think we are to that?
Oh, that's a good question. I mean, what we need is really to know, ideally we would know like what the dose response to infections is, right? And of course, that's a tough one. We won't get an answer to that for a while. So my message, and I think most of us that have been talking about this, we always just keep saying, we don't want to slow down the train, right? It's kind of like climate change. We know enough now. You need to make sure I have this little, actually, I don't know if you can see it. I have my CO2 sensor in my house. I loan these to schools. Everyone's looking at their CO2 levels, make sure your ventilation is good. You can do all these smart things that are really easy to do. So make sure your CO2 levels stay low, so your ventilation's good. Check your particle counts, put your box fans in. I have purple air sensors all over my house. That's gonna lower the risk without knowing anything more than we do. We know that, right? So, I think there's a lot of work to be done. I think we all, if you ask me, and I had a slide on this, I took it out, but like, where is it going? We still need more. And if you ask me, what do we need next? And I think this is where things are going. I know Lindsay's talking about this as well. A lot of people are, is, how does the amount of virus vary as a function of droplet size or aerosol size, right? So that we know where the virus is and what controls that, right? We need to know that too. And so there's other pieces of information we need, but I just would argue, as I have been, and we have been, that, we know enough now. You've seen these papers, I know you follow this, but just assessing risk based on, we know how much is in saliva. So we know how many aerosols come out. So you can calculate risk just from that with what we already know, right? And so they're doing that, like what's the amount of time that you wouldn't want to be in that place, and those kinds of things. So there's quite a bit going on. I mean, and I will call back to Lindsay on this, and that this would not have been doable if it wasn't that she'd already sort of shown the viruses in the smaller aerosols and all the things that we all then were able to build and to move things forward. Don Milton always says, we've been studying the flu for decades and we don't know, we still don't know those things. And here we've been studying this for 8 months and we know a lot, relatively speaking. So anyway, sorry, that's a long-winded answer.
Oh, no problem. Well, I'm going to take one from the chat and then I'll take Timothy Cronin. So Tim, can you unmute yourself while I ask Ross Salowich's question? Is there any knowledge of whether during the very earliest stages of infection, asymptomatic infection, when aerosols are being spread from deep in the person's lungs, whether a saliva test would be effective?
Yeah, they've looked at this. They've done saliva, they've done their nose, right? They've tried to sort of see when sometimes things are correlated, and sometimes they're not. And so, it gets back to this question of, how long before your symptoms show up are you infectious, right? And so that's still being debated. They say that, you're kind of most infectious before your symptoms show up. That's pretty accepted. For how long, still being worked on. But yeah, the saliva test, I don't know that people know yet, like when it, like at what point, if it really was started deep in your lungs. I just don't think we've gotten to that level of detail as far as the, at least that I'm aware of. Lindsay might, I don't know if Lindsay might know about that, but I haven't seen any studies on that yet.
We have some medical people here too, if they want to come in. Certainly happy to have them. Tim, where to go?
Thanks for the great talk. I was curious, and this actually relates to another comment that's in the chat too, about the safety of outdoor dining. If there's a way that you can provide some kind of quantitative reasoning or estimation of why being outdoors is so safe and under what conditions that breaks down.
Yeah, sure. So, based on just epidemiology, like how many times, like China's done, 7,000 cases and 1 was determined to be outdoors. I get nervous saying it's not risky. Obviously it can be. And one of the things we always say is like, let's just say that I haven't eaten outside at a restaurant yet either. But if I do, I'm going to be upwind is what I will tell you, right? So that, that, right? Aerosol smoke, get back to the cigarette smoke, right? It can go, it can carry, and stay pretty concentrated. The general idea though, is that when you breathe out into that huge, massive volume of air, it gets diluted a lot. So the number of, virions in, any air that you can inhale is pretty small. So being outside, then that means that, remember, it's integrated over time. So if you breathe it in, right, if you just got a whiff of it, at that low, you'd probably be okay. But if you sat there talking to someone and you were in sort of what we call their aerosol cloud. I don't know if Lydia Baru was on, but she talks about this cloud and you share the cloud. And if you breathe that for an hour and that person was infectious, that wouldn't be so good, right? So there's all these things to factor in about how much time and which way the wind's blowing and, those kinds of things. But, they say the number that's out there is it's 20 to 1, 20 times more probable you'll get infected inside than out. And there's just a million more cases, thousands of more cases, I should say. Indoors.
Yeah. Lydia is here, so I'm sure if she has some further comments, she'll chime in. And we do have a comment in the chat. And while I ask that one, Ron Prin, if you can unmute yourself and go after this comment. So the comment's from Bruce Walker, and his question is, the box fan with the filter, I guess it's a MERV 13 or is it a HEPA?
It's 13, it's MERV 13, yeah.
Sounds promising, and he wants to know if you can recommend how those would be placed in relation to people. If you have like a 200 square foot room with multiple students, would this be a solution to make the school safe, for example?
Yeah, so there's a lot of discussion of this on the web, right? Because you're absolutely right. If you're taking it and you don't set it up correctly and you're blowing air from an infected kid and putting it in the whole room, right? That's not good. And so there's diagrams that people are setting up, depends on where your windows are, your doors are. The dream is to be able to pull in from outdoors, pump it across and blow it back out the other side. That's the perfect situation. But it's not, you do want to think about, the best places to put them. Either, because it could be bad, right? Especially if you had barriers, like I showed with the plexiglass, you could start to create problems. And so, but in general, there's a lot of schools that are looking into this. There's a lot of homes that have, sort of more socioeconomically challenged, because there's a lot of transfer in homes. And so you put these box fans. I have them in my house because when we had the wildfires, I knocked back the concentrations of particles to 10%, And so again, just filtering it, it's a super simple solution, super cheap. There's a really good article. If you want, I can send it to you, or you can look it up. Just it's the best article that has it all. There's quite a bit on the web too, but it's in Wired magazine. It's like jury-rigged filter, whatever. And they work really well.
So Lydia has a question or point of clarification to make. So Lydia, please unmute yourself and chime in.
Hi, thanks. Thanks for the talk. Kim, just had one question or point of clarification about the drop distributions that you show from Johnson et al.
Yep.
Yeah, because there's really still an open question about where the drops come from, as you pointed out. So I just wanted to clarify that those two peaks were actually caused by different instrumentations and not in fact from a continuum distribution that found a gap in between.
Right. Okay. Yeah. So one was the APS. Yeah.
Impaction and APS, and there's a gap of resolution in between, which gives this impression of having two peaks. So it's part of the big question.
I mean, I have seen other measurements where there is a hint, like if you did the mode fit, there is a hint. It's not that sharp, as you say, but there is a break, and it kind of makes sense that one is more the big saliva drops from your mouth. You know what I mean? They come from different production mechanisms.
Yeah. But
that's the main point that I was trying to make.
Sure. But those are usually another peak at a much higher location, around 10 micron. It's really the big saliva from the mouth. And
It was the bigger mode, right? Yep.
Okay, Ron Prin has a question.
Yeah, Kim, first, thanks for a really interesting talk.
Thank you.
A bit scary, of course.
No, it's not scary.
One is really an observation, but I'll be interested in your response. It seems that part of the problem was a lack of communication between the infectious medical community, the infectious diseases part of it, who were sticking to the notion of the 5 micron and all of that, and took their time before you and your colleagues were able to convince them, and that might have led to confusion in the general public, who would be looking at two scientific communities and saying,
looked like we were fighting.
They can't decide what the truth is, so I won't believe anything.
That is true, and that's why we wrote the paper that came out on October 5th. And I'll tell you that not every medical doctor has bought into this either. They still aren't super happy with us grabbing back the word airborne, but we grabbed it, right? And I look back, because I was like writing this October 5th one, and then I looked, actually somebody said to me, didn't you say this in May? And I had to look back, and I'd said it in May. I used the word airborne 13 times, no one complained, but it's one of those things, you're absolutely right. It looked like we were disagreeing, but what we really weren't. We were just calling the same thing 2 different names. They call everything that, mostly everything a droplet, and those are all aerosols. And they also were under the belief, which, again, it was just sort of medical literature dogma, that they were under the belief that for whatever reason, that 5 microns will fall to the ground, above 5 microns will fall to the ground. That was the part that was really hard to get across, even though we had tons of measurements. But gradually, I'm optimistic. When we wrote this October 5th paper or letter, I had so many medical doctors that had heard we were doing it and asked to sign. They all wanted to sign, and science said, we don't want 100 signatures or whatever, right? So we ended up going with just we were trying to make the point, like, it's an interdisciplinary. We crossed all the way from virology to infectious disease, occupational health, to viruses in the air, to aerosols. And so that was our message. But yeah, getting to back to your point though, it was painful is what I will say. It made us crazy, you know, made us a little crazy that it was, they didn't really want to budge too much. So, you know, it's one of those things. And I would have let go, to be honest with you. And I kept saying, like, I would just let go back to my day job, climate change, right? Except that people were dying because of this misinformation, right? So we just kept pushing, and I think we're really close. And
Yeah, there's another area where the two communities should be coming together, and that is to try to work out this issue of the relationship between the dosage of virus and the actually not being able to fight.
Yeah.
Very intensive. It'd be really nice to be able to quantify that. And again, those two communities have got to come together. Folk like you, and then people in the infectious diseases who are looking at what goes on once they're in the body. But
yeah, and I think that's to me, that's the silver lining of COVID-19 that I've seen so far, is we are now talking. We found the open-minded people that are ready to work together, and we're going to not just fix COVID-19, we can go fix the flu and, you know, but we can go back in time, because a lot of the assumptions were probably not correct then either, right? And so I think that we now have broken down those barriers through this process, as painful as it may have been. Not for everybody, but we found out sort of that interdisciplinary team that you need to solve a problem that's this complex. I'm super excited. I'm building an instrument. I have funding to take our single particle mass spec and mass spectrometer, and we're going to be looking for the amount of virus in individual particles online. So that I can't wait. And so, yeah, it's pretty neat to bring it all together.
very good.
I'm going to take Chair's prerogative to just ask one more question, because I think it's on a lot of people's minds. And since it's after 5, then we'll just give Kim another round of group applause and let her go. Are the standard cloth masks in stores good enough is the question. And you know, what about the aerosols? Do they actually get them? And by the way, I personally have been putting a MERV 13 piece of filter paper in my mask since the very beginning. As long as it doesn't have fiberglass, non-fiberglass, it's available, you know, as sheets. You can buy it as sheets on Amazon. But what should we do about masks? I know several of you have worked on masks.
Yeah, so we have, you know, I'm gonna toss this one. We've got the world's expert on masks who's on the line, Lindsay. She's been testing these things, and a paper just came out. I don't know if you saw it. Like, actually, you know, papers are getting better and better. Some people thought you could just turn on aerosol instruments and measure masks, and some of those were not. They were heavily flawed. But now they're starting to get better and better. To your point about, you know, the filtering efficiency. So, Lindsay, want to take this one?
Sure, I'd be happy to. There were some papers that were rushed out by non-aerosol scientists that have had to be retracted or corrected multiple times, but there is general consensus among the aerosol science labs that are conducting these types of studies. For example, John Volkins at Colorado State, Nina Vance at the University of Colorado. I know others have looked into this too, and my lab also, but generally almost all cloth masks, even just a t-shirt, will block about half of particles in the kind of 1 to 2 micron range. Once you get up to 4 to 5 microns, you're blocking 80% or more of those, even with the just single layer, nothing special. And if you do, and you know, we think that even though the virus itself is 0.1 microns, it's going to be present in respiratory droplets that are larger. Even after they evaporate, there's still a ton more salts and proteins there. So, and from what we've seen in other studies, the action is kind of in the 1 to 10 micron range. And so if our cloth masks are, okay, they're not an N95, they're not, you know, 95% efficient and better, but, you know, I'll take a reduction in half of my exposure over nothing any day. And once you take multiple layers, then you can easily get up to kind of 75, 80%. And then of course, if everyone's wearing masks, then you get that additional kind of source control and exposure reduction at the same time. And to speak to Susan's comment about MERV 13 filters, that's great. We have, if I go on the airplane, I put on my mask with double layer of HEPA filters in there. HEPA filters are 99.97% efficient at the most penetrating particle size of 0.3 microns. So those will block everything. But really the key at this point becomes fit. If you have any gaps, of course, you just short circuit that.
Well, let's just thank Kim, and thank you everyone, including the other experts who joined in, and thanks for your service to the nation.
Yeah, thank you. Thank you.